don't know why, but I feel like this music is super appropriate for an EVCC, just having the slideshow play in the background. There we go. Hi, welcome back to Chem 161. Oops, I meant to go over here. What do we got going on this week? So we're going to finish Chapter 2 this week. We're probably going to finish it, let me see. How many more slides do we have? Oh, we have a lot more slides, so probably Thursday is where we're going to finish it. A lot of this material is review, although the history stuff we're doing is probably new. So we're going to breeze through most of it. Quiz number 1, I posted it last week. It is due on Thursday the 21st. Make sure that you get that in by the deadline. Lab Worksheet number 1, which we haven't really talked much about, and there's really not much for me to talk about other than, hey, this is glassware you'd use in the lab. We're not in the lab. That is due on Wednesday, so that's tomorrow. So if you have any questions about the lab, please ask me in the Discord. I'm happy to answer those questions there. There's really not much for me to say other than what is in the lab worksheet. I do have documentation that tells you how to download the copy of the worksheet, then how to export it as an XLSX file, and then upload it into Canvas. Make sure you are following those directions. Do not request permission to share the file. You will not get it. You can make your own copy. That is something that is available because I've set it up for you to do that. And I should have gone through all that last week, I believe. So if I didn't, let me know. We're going to resume talking about the nuclear structure of the atom. We left off on the gold foil experiment where I had put on the screen something like this. Oops, hold on. That didn't show up. There it is. And I had said, scroll, that either our atom was a solid orb that all the particles would just bounce off of, or it was this nebulous area of positive charge where our alpha particles that we're firing would just go straight through. Or maybe it was some in between where I have this nebulous part, but then I have a small solid part in the middle where most of the stuff would go right through, but some of it would get deflected at random angles. And so the gold foil experiment was done to show what the structure of the atom was like and eliminate other possibilities. And so what they found was that this model matched most with their observations. Not everything went straight through. So that eliminated this option. So the plum pudding model was thrown out because stuff did get deflected. However, not all of the stuff was deflected, so this model is no good either. Atoms were not a solid wall that was impenetrable by particles. In fact, most of the particles went sailing through, which indicated that the nucleus of the atom must be very, very, very tiny indeed. So I do have a video of this that I'm going to show you. However, if I play the audio, it will get copyright struck because this apparently is, let's see here. So this is Backstage Science, which is, I mean, this video has been viewed 2 million times and they have 60,000 subscribers. So I'm going to play the, actually I'm going to play the audio anyway because the audio is kind of important. So we will figure that problem out later on with, I gotta make this smaller before I do this. There we go. Alright, so let's watch this and we'll see the gold foil experiment in action here. I'm just going to put the audio down kind of low. You know, we'll even turn on the subtitles. Not in Portuguese, though. That's not what I want. English. Oh, they don't have them in English. I don't want auto-generated because it's going to sound stupid, so we'll just turn that off. All right, so let's see the Rutherford experiment in action here.
At the time he carried out the experiment, the atom was thought to be a blob of positive charge with negative electrons embedded inside it. Now Rutherford set up an experiment to direct a beam of alpha particles, which he knew to be heavy positively charged particles, and we now know to be the nuclei of helium atoms, through a very thin gold foil. The brass can in the centre of the picture contains a small americium-241 source producing alpha particles. Most of the particles are absorbed in the brass. There is a small opening producing a beam of alpha particles. They pass through a gold foil, which is about 1.5 microns in thickness, and they are then detected by one of the two detectors set up behind the foil. One of the detectors counts particles going straight ahead, which is the majority, and we count a rate of between 1 and 2,000 per second.
So this is the F means fixed. This is the camera that is directly on the other side of the beam. So you can see here, if I go back just a few seconds here, that this thing is firing tons of particles at it. 1,000, 2,000.
The second counter.
Here's the other counter.
To measure the scattering rate as a function of angle.
And
now,
it's much less often.
The experiment he and his colleagues carried out was very laborious. It involved them sitting for hours in a dark room, holding a tiny fluorescent screen and looking just by eye for flashes of light on the screen. We've replicated that with modern detector technology.
So the way that this is going to work is that the mobile detector is set up on the side somewhere, and it is connected to a circuit that rings a doorbell. And so every time a particle hits the mobile detector, in other words, the nucleus of an atom deflects an incoming alpha particle into the detector, you'll hear the doorbell. And so that's going to visually look like this. Well, that's what it sounds like.
In its current position, behind the foil, it will measure one count every few seconds.
Bonk. This is how often it's coming through.
Most of the gold atom's empty space, so the alpha particle just goes straight through, doesn't see anything, and goes through in a straight line. Occasionally, one of the particles will come close enough to the nucleus of the gold atom that it will be deflected by the electric field from the positive nucleus. If it comes at a glancing blow, it will be deflected through a small angle. If it hits it head on, it will just bounce straight back. And it's fascinating, I think, to them that this was telling us something very important that we didn't know about the very deep structure of matter. It showed that the atom had a heavy nucleus with mostly empty space with electrons distributed around it, which is exactly the picture we now have. It was also the start of particle physics. What Rutherford was doing, and what we're doing here, is taking a beam of particles, firing at a target, looking at the way the particles are scattered, and from that deducing what was going on inside the target.
So, two things to note there is, one, this is a very simple experiment in theory, but you learn so much. And two, working in this lab would be miserable because this goddamn doorbell keeps going off every few seconds. So, I don't know if I could deal with that. But it's really powerful what you can do with simple experiments to explore the fundamental nature of matter. So, on the right here, we have concluded that the structure of the nucleus looks like this. Oops, that's not what I meant to do, sorry. We have this tiny, 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 tiny positively charged part in the middle. That's called the nucleus. And then the electron cloud is the part around it. We're going to spend a lot of this quarter describing the electron cloud in as great detail as we can. And the reason for that is because the electron cloud, or the electrons that are flying around in it, are basically the entire premise behind chemistry. Chemistry happens because of the electron cloud. The nucleus is cool and all, but it's not what we're going to be studying primarily in this class. All right. Now, just a brief primer on radioactive particles. We're not really going to touch on radioactive particles again until Chapter 20, which is Chem 163, and I'll review these then if we get to that point in that class. But here are the particles that were used in the experiment. Well, one of the particles that was used in the experiment. That was the alpha particle. What is an alpha particle anyway? An alpha particle is actually this. It is a helium nucleus stripped of all its electrons. And the reason that it is a helium nucleus with no electrons is because it's ejected from the nucleus of whatever atom is in our radioactive source. So in the video, it was americium. I don't remember. I think it's 241. I forget what isotope it is. Radioactive isotopes will spit these particles out in an attempt to get to a more stable structure. For instance, maybe the nucleus has just too many protons in it, and those protons all repel each other, right? And no number of neutrons will stabilize the nucleus. Well, a way to fix that is if the protons repel, toss out some protons. That will alleviate some of the stress on the nucleus. Alpha particles tend to be the most common particles expelled from the nucleus because a helium nucleus is extremely stable. A beta particle is just an electron. Yes, a nucleus can eject electrons. Where do the electrons come from? We'll talk about it in chapter 20. So you'll have to wait 2 quarters for that. Or you can go look it up on Wikipedia. But yes, you can get electrons out of the nucleus. Hint, they come from neutrons. What? And then a gamma ray is just high energy photons that come from the nucleus rearranging itself. Think of like if you have something that's really, really heavy and it collapses, it releases energy when it hits the ground, right? And it will be more dense as a result. The nucleus can be in a state where it can, quote unquote, collapse inward, where things rearrange and reshuffle and it gets closer together and more dense. As a result, a gamma ray would be emitted from that instead of things like sound or vibrations from dropping objects on the floor in the macro scale. Now, how the heck do you tell these particles apart? The one thing that they have that differentiates them is their charge. Alpha particles are positively charged. Beta particles are negatively charged. Gamma ray particles are just photons. They have no charge. So if you send them through an electric field, they would diffract in the following manner. The alpha rays would bend towards the negative terminal on your electric field, and the beta rays would bend towards the positive terminal on your electric field. Gamma rays would move through unimpeded because they do not have a charge on them. Now, because electrons are much, much lighter than a helium nucleus, the beta rays get bent much further. So, not only did we learn a little bit about what charge each of the particles is, we also learned about their mass relatively. Alpha particles are much heavier, they don't bend as much when disrupted by the electric field. All right. So, what we have learned from all these experiments that we described on Thursday last week and then the Rutherford experiment today is that the following must be true based on our findings. An atom contains a solid tiny center that we're going to call the nucleus, and the nucleus is extremely dense. When I say extremely dense, I mean like holy shit dense. In fact, if I want to load my 163 slides here for you, just real quick, just to give you a preview of just how dense this is. Hold on. Because I'm writing these slides for my class here. Will this appear on my screen? Oh, wow. So what do I have to do here? So if I go like this... That went off a little too quickly there. But if you read this problem here, if I have only iron nuclei in a teaspoon, what will it weigh? 1 billion metric tons. This is how dense the nucleus is. If you only had nuclei in a teaspoon, it would weigh billions upon billions of tons. And there's only one logical response to that. That's not a window I expected to see there. And then I got the little, like, gaggy shock noise there again. So I have the wrong slide, so hold on. There we go. So in 163, you get shit like that, where holy crap dense. So it's going to be very, very difficult for us to do anything with a nucleus because it's so dense, the energy that holds it together is so high. So the nucleus is not really the interesting chemistry. We're going to do stuff that's much lower in energy, much more reasonable, that we can work with. And so that's going to be the electron cloud. And so that's going to be our interest in the upcoming chapters, is this. So electrons spin around the nucleus. They are quite far away from the nucleus, and the atom, as a result, is mostly a void of space. There's nothing. It's just completely empty. Now, an interesting thought about that is, if you are made of atoms and everything around you is made of atoms, and everything around you's density is not 1 billion tons per milliliter, that must mean that everything around you, too, is also like 99% empty space. It's extremely void of matter. And yet you can see stuff. Like if I'm looking at my computer, I'm looking at my table, I'm looking at my hand. It's not completely empty, right? And in fact, if I put my hand on the table, and you can hear me doing that, my hand doesn't go through the table, despite both things being mostly empty space. Why the heck is that? We can actually justify that by drawing out pictures of atoms here. So here are going to be atoms of one object, and here are going to be the atoms of other objects. Now, on each of these atoms, I'm going to draw the nucleus. It's just this blue dot in the middle here to represent that these are our nuclei, and they're extremely tiny. If I have one object collide into another, you'll notice that the nuclei don't get next to each other at all, right? What ends up bonking into each other is this right here. So the electron clouds interact. So if you come to contact with another object, like say my hand hitting the table here, the electron clouds on the atoms in my hand and the electron clouds of the table interact. And what charge are electrons? Well, we've already learned that they are negative. What would two negative things do to each other? Well, they repel. So the force that you feel pushing back against your hand and preventing it from passing through the table is actually the repulsion of the electrons and the electron clouds of the atoms of the table. If you've taken a physics class, this is called the normal force. The normal force is just the result of your electrons being repelled by whatever else's electrons are holding you up or holding you away or back or what have you. So despite us being almost completely empty space, we actually interact with matter in a way that appears to us to be normal. Now, the one thing I didn't talk about on this slide was that protons are in the nucleus. We already knew that protons were positively charged based on the Rutherford experiment and how the alpha particles got deflected by them and pushed away and didn't get attracted and or like combine with them or something like that. So there's one last thing to talk about, and that is the neutron, because the atomic theory that we have at this point is, I have a bunch of protons in the nucleus, but protons repel each other. And so there is an issue regarding that protons can't just be by themselves in the nucleus. They would repel. Electrons repel. There's just as much charge for protons in the nucleus as there are for electrons. How do we stabilize this? How do we keep the protons from repelling? And the answer is, there is this third particle called the neutron. And what the neutron does is the neutron stabilizes the presence of other protons. Protons do repel, but adding in neutrons creates an interesting phenomenon. It's called the strong nuclear force, which is one of the fundamental forces of nature. Strong nuclear force, weak nuclear force, electrostatics, and gravity are the 4 fundamental forces. The strong nuclear force is just responsible for holding the nucleus together. It only works across nuclear distances. And the part of this that is responsible is the presence of the neutron. The neutron does not have a charge, but instead it engages in the strong nuclear force. Now, because neutrons don't have any charge to them, where is it? There we go, not have a charge. That means that it is possible for you to have varying numbers of neutrons. And so this is what's called an isotope. Two isotopes, or two atoms are isotopes of each other if they have the same number of protons but different numbers of neutrons. On the screen here, you can see hydrogen, deuterium, and tritium. These are common names given to different isotopes of hydrogen. Hydrogen normally is just a proton and an electron, and they spin around. This is the most abundant form of matter in the universe. Deuterium, which is also known as hydrogen-2, is a proton and a neutron coupled together in the nucleus, and there's an electron spinning around them both. Tritium is 2 neutrons and a proton. Tritium is actually very radioactive. It doesn't last like this for long. And the reason for this is because neutrons and protons stabilize each other, but too many neutrons will actually become unstable. Neutrons themselves don't stay as neutrons for very long. The reason being is that neutrons are actually the combination of a proton and an electron together to make a neutron. We do crazy particle physics shenanigans to change the quarks that are present in the proton to make it a neutron. If protons aren't present to stabilize this, they decompose. And so in tritium, what will end up happening is one of the neutrons will decompose, and I believe that it turns hydrogen-3 into helium-3. More on that in nuclear chemistry in Chem 163. But for now, what you need to know is that isotopes follow this rule. Same number of protons, different number of neutrons. Same Z, different A. And we'll do examples of that in a little bit. All right, there's our picture of the atom. In the middle is the nucleus. We've talked about the nucleus. Around the outside is the electron cloud. We've talked about the electron cloud a little bit. Excuse me. A major focus of Chem 161 is going to be electronic structure. And you can see in this diagram that I've drawn these little orbits that my electrons are revolving around. This is a common caricature of electrons around a nucleus. That is absolutely false. And the reason that it's absolutely false is because it's very, very simplified and is not actually what happens with electrons. Electrons do not follow constrained rings like planets do around the sun. Electrons follow a very chaotic path because there are so many other forces acting on them. They are so light and they are repelled by other electrons all the time. So their path is unpredictably confusing. Also, something to note is that the diagram on here is very exaggerated. This nucleus is 52,800 times too big. And so what we should actually have is, if the nucleus was this large, which on my screen it's about an inch, that means that I would draw the electron cloud 52,800 inches away, which is, I don't even know what distance that is. 52,800 inches to miles. That would be roughly 0.8 miles. So if I were to leave the nucleus this size, the edge of the electron cloud would reach a distance of 0.8 miles across. In other words, I live right next to Boeing. My electron cloud would be roughly the distance from Boeing to I-5. Which is insane when you think about it, right? Like, that's how empty the atom is there's going to be this 1-inch blob somewhere between Boeing and I-5, and the rest is empty. Yep, that's atomic matter. Sometimes the truth is stranger than fiction. All right. In the nucleus are two different particles that we've talked about, protons and neutrons. You may hear the term nucleons come up, probably not until 163, chapter 20. Now, we've also briefly mentioned charges here, so I've got positive and negative charges. Opposite charges attract, like charges repel. This is going to be very important for us to know when we're studying chemistry, because chemistry involving electrons is going to basically just be applied physics. Positives and negatives attract each other. Double positives repel, double negatives repel. So a lot of chemistry is going to be, okay, where are my electrons on this molecule and where are they at on the other molecule? Can I arrange such that the electrons on one molecule orient toward the part of the other molecule where the electrons are not, for example? And if so, you may be able to form a bond or a reaction or something interesting that way. And organic chemistry focuses on this a lot. Where are the electrons? Where are they not? Will a reaction occur because of this? So we're going to care most about electrons, which is why we're going to start talking about them in Chapter 3. Now, the neutrons, like I said, their role is basically nuclear glue. Hold the protons together, hold other neutrons together, hold the nucleus together. The neutrons are needed to do that. For any atom, we are going to have the same number of protons and the same number of electrons present. The result is that an atom is electrically neutral. So if I have an atom by itself, the positives and negatives exactly cancel out, and I should experience no net electric field around the atom. Now, localized, if I were to get very close to the nucleus, excuse me, sorry, I'm yawning as it's 2. If you get very close to the nucleus, then yes, you would be repelled by the nucleus if you're positive, or attracted to it if you're negative. If you got really close to an electron cloud, or an electron in the electron cloud, then yeah, you would interact with that negative specifically. Say if you were another electron bumping into an electron in the electron cloud. But overall, on average, the outside influence that you would feel would be electrically neutral. There'd be no electric field. The positives and negatives would all cancel each other out. Now, this is not true if you have an ion. Ions have different numbers of electrons and protons, and thus there is a residual electric field that is interpreted by us as what we call charge. We're going to talk about ions in Chapter 4. So just keep that in mind for now. You probably already know what an ion is from 140. All right. Here's our summary for atomic theory. This is everything condensed in one slide. So basically, atoms are tiny particles that make up matter. All the atoms of a given element are chemically identical. Note that I use the word chemically there. What that basically means is number of protons and number of electrons. Neutrons don't participate in chemistry. They just change the weight of a molecule. So physically, they may be distinct, but chemically, they will all be identical for a given element. For our atom, there are 3 parts. Protons and neutrons are in the nucleus. Electrons are outside the nucleus. Those particles have fundamental charges. Protons and electrons are positive and negative. Neutrons have 0 charge. And then finally, isotopes are going to be this interesting thing that we can study later on. They have varying properties, both physical and I don't want to say chemical because that's not what I can. Sorry, nuclear is what I'm saying. So when we get into nuclear chemistry, different isotopes will have different properties that we can look at. But chemistry that we're going to be studying for 19 chapters up until we get to the radioactivity stuff, isotopes are going to be chemically identical to each other, provided they're all the same element. All right, any questions, let me know. That is the overview of atomic matter. All right. Let's start refining our knowledge of atomic structure into the periodic table, which we're all familiar with. So the first thing that we want to do is we want to identify the atomic number on the periodic table. If you've taken this class or if you have taken a class with me before, you know which periodic table I use. That is this one right here. Oops, if I can click in the chat there. This is P-table. P-table is probably the best online table that I'm aware of. I'm sure there are others, but this is probably my favorite, and it's definitely the favorite of students because I got this from students. So, P-table has all the information that you'll need for all of the elements that we will use in chemistry. Do not commit shit off of P-table to memory. It is there online for you. You will make Mendeleev mad because Dmitry Mendeleev, who wrote the periodic table, created it for the explicit purpose of not having to commit things on the periodic table to memory. If anyone makes you memorize the periodic table, they are stupid. You have my permission to slap them, even if it's another instructor. Don't actually do this. If you ask me, I will slap them for you. I hate when people make students memorize the periodic table because all this information is just available for you. So there are things that we're going to want to commit to memory just because we're going to use them a lot that are related to the periodic table, like what do these numbers at the top mean? Or what do these numbers over here mean? Meanings are important to memorize, but like, do not memorize that the element 48 is cadmium. Like, there are better things to use your brain cells on. You'll notice that on the periodic table, in all of the boxes that you can see here on my slide, there's a big number at the top left. There will always be an integer value in the top somewhere. The alignment may vary. On this periodic table shown here and also on P-table, it is the top left, but some may center this. It doesn't really matter. The point is that number that is in the very top is called the atomic number. And the atomic number tells you the number of protons an atom has. This is a definition, because counting is not something that contains error. We have defined every atom by the number of protons in its nucleus. If you have 1 proton in your nucleus, congratulations, you are a hydrogen. If you have 2 protons, you're helium. If you have 3, you're lithium, and so on and so forth, all the way up to 118. Some examples on the screen. All sulfur is 16 protons. All carbon is 6 protons. If you change the number of protons somehow, you change what the element is. Now, that is not trivial to do, to change the number of protons in the nucleus. This is why we chose the number of protons to determine what the identity of an atom is. If we had chose electrons, elements would shift all the time, because removing electrons is trivial compared to removing protons or adding protons or what have you. All right. If you have a neutral atom and you arrange the electrons around it, there will be some electrons closer to the nucleus and some electrons that are farther from the nucleus. In each of these cases, we can either remove electrons because they are being repelled by electrons that are closer or whatever, or we can add electrons because there is physical space that we can put extra electrons in there. When you do so, you will end up with an ion. The relationship that I want you to remember is this one. If you have an atom and you remove or add electrons to it, you will always create an ion. The reason being, atoms are electrically neutral. They have the same number of electrons and protons. If you change that number of electrons, you create an ion. Now, if you change the number of electrons an ion has, you may or may not create an atom. For example, if I have 10 protons and 11 electrons, and I add an extra electron, I'm just making another ion. Now, depending on which direction you go with your charge here, you will create either an anion or cation. Anions have more electrons, so they become more negative. Cations have fewer electrons, they become more positive. So adding electrons to atoms forces them into becoming anions. Adding electrons to removing electrons from atoms causes cations to form, which are positively charged. So cations are positive, anions are negative. Here's how I remember that. If you write out the word cation, the positive is baked into the word itself, and anion is the other one. The other mnemonic that other instructors use is cats have paws, positive, or cats are positively the best, or I don't know. I don't like that analogy as much, so I use the cation one with the positive. Anions are the other thing, so they're the opposite. Now, it's very easy to get confused when determining do I have a cation or an anion, because what you are doing is you are adjusting the charge by removing something that has a negative charge. If you take away electrons, you are taking away negatives, and the result that is left over is a positive. If you add negatives, the charge on your particle becomes more negative. So think of it as doing addition or subtraction with negative numbers. What is 5 minus negative 2? It's the same as adding positive 2. So if I remove 2 electrons, I'm increasing the charge by positive 2, and so on. Again, this should all be review. But if it's not, that's how we do calculations with electrons. Be very mindful of that, because it's super easy to just flip this around, do it backwards, and you get the wrong number, and everything falls apart. All right, as an example, if I have sodium and I was removing an electron from it, what would I write? So, here's my sodium. That's not what I meant to do, because that's the answer. Trying to select the pen. There we go. If I were to count the number of protons and electrons on sodium, here's what you would do to determine the answer. So let me go get PowerPoint, or not PowerPoint, but where is it? P-table. Boop. Give me a second to size this. There we go. So here's P-table. I just hit the mic. Great. First, let's find sodium. Remember that the atomic number tells you how many protons sodium has, or any element. So I'm going to start with that. So sodium has 11 protons. P plus is the symbol for proton that I use. I'm not sure if that's universal, but this is fine for now. We also know that neutral atoms have the same number of electrons. So sodium has 11 electrons in it too if it has 11 protons. So there you go. Now what we're going to do is we're going to remove an electron like the problem is saying. So let me do that in a different color. Oh, for fuck's sake. Don't know why I did that. There we go. I have removed an electron because that's what this problem told me to do. So what do I form? This would be sodium with a plus charge. And you can see that the total charge would be positive 1 because I have positive 11 from this, negative 10 from that. The sum of those two together is positive 1. And visually, that would look like this. Now, you can see that the electron cloud actually contracts when we have removed an electron. That's because the nucleus is pulling all those electrons, and it's easier to pull 10 electrons than it is to pull 11. So it can hold on to them a little closer. Again, the nucleus is exaggerated in this picture. What about for chlorine? What do I do with chlorine if I add an electron? Same thing. Chlorine, we go to the periodic table, and we would find that it has 17 electrons and protons when it's neutral, because it's element 17. Why didn't that stick there? There we go. So there's chlorine. I'm going to add an electron because the problem was asking me to do that. I now have one more electron than protons, so the charge that I get is negative because 17 positives and 18 negatives added together would give me negative 1 as a total overall charge. And that looks like this. And then when you add electrons, the electron cloud gets bigger because the electrons all repel each other and they need more space to put an extra electron in. All right, I think that that's a good spot for a break. I need to get up and go chug water or something because I'm just sitting here yawning like crazy. So we're going to go back over here. Let me put the timer on the screen here. We'll come back in 10 minutes. Let's listen to some more Paradise Killer, or you guys will, while I go drink some water. So I'll see you in just a little bit. All right, there we go. Welcome back. Let's continue talking about ions a little bit. We're going to move into isotopes here. So generally speaking, on the periodic table, we can separate our atoms into two categories, metals and nonmetals. Metals tend to form cations, which means they give away their electrons. Nonmetals tend to form anions, which means they accept electrons. And generally speaking, metals will pass their electrons to nonmetals because that's the order of what these elements want to do. Now, ions behave differently from elements because of their electronic structure. Adding or removing electrons changes the stability of the ion or atom that we're talking about. Potassium metal, for example, very unstable. Its valence electrons will hop ship very quickly on contact with water. And in doing so, we create a very violent explosion. We're going to show why this is in Chapter 3. Potassium ions by themselves are relatively inert. These are things that would be dissolved in like salt, for example. So if you had KCl and you dissolved it in water, you don't get an explosion. In fact, what you just get is a mess, really. Your water will dissolve it. The KCl is now floating around, and if you taste it, it tastes like KCl, which it turns out is not very good. So again, we'll talk about this in Chapter 3. Ions and atoms are very different from each other. Sometimes we want to have ions form, and we'll form particular ones. Sometimes we want, or sometimes just atoms will form particularly noble gases. Again, this is all going to revolve around electronic structure, which we're going to get to later on in the quarter. We can use symbology to identify atoms that we are working with, and in fact, we're going to be doing that a lot in this class. And the symbology that we're going to be using requires the use of these two variables. So the first variable is Z. Z is the atomic number. You're going to see Z a whole bunch this quarter. This is something that we did in 140, and you're probably just like, well, why did we assign it a variable? You'll see why. A is the mass number. And A is the number of protons and neutrons added together. Z shows up right here inside A, because Z is the number of protons. So Z can never be larger than A, because A is two numbers added together. So we're going to want to keep these variables in mind, because we're going to be writing symbols using these variables in the following manner. We've already learned that protons and electrons are the same in a neutral atom. So the atomic number does tell you that information. We may change the number of electrons, but I had to describe that to you in a given problem. So here's what we're going to do. We're going to talk about the atomic mass later, so don't worry about that just yet. We're going to arrange Z and A around our elemental symbol, which I've written in curly brackets E. So this right here, we're going to replace this we're going to replace the whole thing with the symbol from the periodic table. There are no curly brackets afterward. We're going to replace the whole thing. So whatever element we're looking at, we're going to replace that with, I don't know, like if we're talking about carbon, we put a C there. If we were talking about hydrogen, we put an H there. We're talking about lanthanum, we put capital L lowercase a, for example. So that's going to be our first step. Get rid of that curly brackets E and replace it with whatever chemical symbol the problem that we're asking about is looking for. Step 2, we're going to look at the atomic number of that element that we're working with. We're going to write it as a subscript right before it. Then we're going to write the mass number as a superscript right before it too. They stack vertically on top of each other like this. However, when I am typing something into the computer, like for a Word document, this is unfortunately what my text looks like because I can't get two things to stack on top of each other. without doing like some crazy formatting that I don't have access to at home for free. So if you see something that looks like this, it is intended to represent this. I just can't typeset it correctly. All right. So those numbers go in those positions, and if you have them in those positions, then what you've written is the isotopic notation symbol. Now, if you have a charge, you can indicate the charge as a superscript after the chemical symbol. But if there is no charge present, just ignore it. Leave that space blank. Don't enter a 0 there for charge. So this is known as isotopic notation or complete chemical symbol notation according to your textbook. I just write this. I write ZAE notation. So what I want you to do is for this example here, to the best of your ability, type the ZAE symbol for a carbon atom with 6 protons, 6 neutrons, and 8 electrons. So in the chat, go ahead and type that. And we'll go over the answer in just a second. There you go. That's good enough for me. So for our carbon atom here, we have 6 protons. So we're going to put a 6 in the front right here. Boop. We have 6 neutrons. Remember that the mass number is protons plus neutrons. So since we have 12 total protons and neutrons, we'd put a 12 up there. And then the charge would go in front. Charge is just protons and electrons considered together, which would be something like this. So I have 6 protons and 8 electrons for a total of -2. So we'd put the -2 right there. All right, very good. What I want you to do is try and do these 3 symbols based on the information that is present, and then fill in the chart to the best of your ability. Obviously, typing this in the chat is going to be really frustrating and obnoxious in terms of formatting, so type in whatever you can. We'll go over all the answers in about 5 or 6 minutes. In any case, let me know when you are finished so we know to continue. Let's do 2 more minutes, and we'll go over the answers. All right, let's go over the answers here. So I do need to go to this slide, unfortunately, for these top ones, because there's nowhere else to write them. Get rid of these drawings. All right, an atom with 7 protons, 8 neutrons, and 6 electrons. So from all of this, we would say that, okay, well, Z is 7. A is these two together. So that'd be 15. And then the charge would be 7 positive minus 6 negatives would be positive 1. So we can write that like this. Well, what's element number 7? We got to go to the periodic table, which I have closed, unfortunately, but I have my periodic table over here. Let me go grab it. I have a laminated one that I just stole from the lab or something. I don't know. So element number 7 is nitrogen. So our symbol that we would write would be this. So we go nitrogen, put Z there, we put A there, we put the charge up there. I'm just looking in the answers to see if anybody did that one. Or you're doing the table or whatever. I don't know. Okay. For the second one, the problem just tells us, okay, Z is 25, A is 55, and the charge is... I can't actually read that on my screen here. Is it 2 minus? Yeah, 2 minus. So we just fill all that in. So 25, 55, 2 minus. What symbol is this? What is element 25? It looks like it's manganese. There you go. All right, an atom with the same number of protons, neutrons, and electrons, and A equals 36. So I have... that, and I know that A is 36. A is the sum of protons and neutrons. So that means that this must equal that, and therefore X is 18. So that means that Z is also 18, and the charge is 0. So this symbol would be that. All right, so those are those problems. Let's go back over to here and start filling these in. So, looking at the periodic table for chromium, chromium is element 24, so I got to do this. And then based on the charge, I could say, well, okay, if I have a charge of 4 plus and 24 protons, I must only have 20 electrons. And then I can fill in the ZAE symbol. So Z is 24. A is 20 protons plus neutrons, which would be 24 plus 27, so 51. This is chromium with a 4 plus charge. There we are. All right, the next problem I have protons is 16. Protons plus neutrons is 16 plus 18 is 34. Element number 16 is sulfur, so we'll write that down. And then the charge, well, these have the same number, so the charge will be 0. And then down here, Ag is silver. Just fill that in. Z is the number of protons. A is protons plus neutrons, so I need to do 106 minus 47. I do have a calculator over here for this, so we do not need to do mental math. And then finally, the charge is going to be the difference between protons and electrons. All right. Should be pretty straightforward. We're all set. All right, let me know if you have any questions about that. Earlier on, we talked about how isotopes have varying number of neutrons. Here are a set of isotopes of boron. So if I remove this, and I said, okay, number of protons, number of neutrons, and I sum these together, so, or not sum them, but I compiled them, I would get something like this. That's not what I meant to hit. There we go. So to identify if something is an isotope of something else, what you need to do is you need to look at all the Z's and meet these criteria. The criteria are same Z, different A. So the definition of an isotope is any atom that has the same number of protons but different number of neutrons as what you're comparing it to as an isotope. So these would all be specifically isotopes of boron because they all have 5 protons but varying numbers of neutrons. And you can have as many neutrons as you want. You could have 5, you could have 2, you could have 0, you could have 100. It would still be an isotope. Now, whether it exists in reality is going to matter based on how many neutrons there are relative to protons. And that's not something that we can predict super easily. In 163, I will show you a chart that just has all of the record of any isotopes that have been synthesized or observed or found or whatever. And all that information is recorded. But on paper, you can have any isotope you want. All right. Now, we have some definitions here. An isotope is a naturally occurring isotope if it has a half-life that is very, 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 very long relative to the age of the universe. In other words, like 4 billion years or so, or longer, would be what we call a naturally occurring isotope. The reason that that number was what we've selected is twofold. One, uranium is very, very, very weakly radioactive, and it has a half-life of 4 billion years. 2, the age of the Earth is roughly that number of years. So if something is naturally occurring, that means that we have to be able to observe it in nature, right? So if an isotope is naturally occurring and it's radioactive, but has a really, really, really slow half-life, shorter or slower or longer than 4 billion years, we'll be able to observe it. We can go dig it up in the ground and we'll be like, oh, there it is. So we can do this with uranium. Uranium is very abundant. And we can find uranium in the ground, and it is radioactive. It will slowly decay over a long period of time. Now, an isotope that is synthetic is one that is much more unstable than one that is natural. And what this means is that a synthetic isotope must be made. It may have existed at one point, but because the half-life of it is so much shorter than our threshold of 4 billion years, any trace amounts of it would have disintegrated away. So, for instance, cobalt-60. Cobalt-60 is a very radioactive isotope that is used for various applications, but no cobalt-60 exists on Earth. Naturally, anyway. You have to make it. And the reason for that is cobalt-60 has a half-life of like a few hours or something like that. I was looking this up the other day. Let me look at its half-life. 5.3 years, so that's not a few hours. But the point is, if I made some cobalt-60 billions of years ago when the planet was formed, if I lose half of my cobalt-60 every 5 years, and billions of years pass, I'm going to have the amount of cobalt-60 down to the point where there is 0. I will never detect it. There's so little. And again, more on this in Chem 163, because apparently this is the we'll talk about this in 163 lecture. All right. Last thing I think that we're going to have time to do today. Well, we might get into mass spectroscopy because we end at what? 4:20 or so, so we have 30 minutes or so. Oh, yeah, maybe we'll get to that. Okay. So the next thing we're going to do today then is we're going to talk about how to calculate the atomic mass on the periodic table. This is something that we did in 140. And the way that we do this is we introduce a unit called the atomic mass unit. The atomic mass unit is useful because we don't really want to deal with masses of atoms in grams. It's too obnoxious of a number. Instead, what we do is we use atomic mass units. And specifically in 140, we use just the ones digit. And so we said an electron weighs 0, a proton weighs 1, and a neutron weighs 1 in AMU. For Chem 161, 162, 163, this relationship is still okay. However, at some point, excuse me, at some point we are going to want to use those other digits because it's going to be helpful to us to do so. So we will get to that at some point. For now, if you're just trying to estimate the mass of an atom in AMU, yeah, whatever A is, the mass number, that'll be the mass of the atom in AMU, and that's good enough to a first-order approximation. Later on in this chapter, so we might get to this today, we might get to this on Thursday, when we're weighing atoms individually, we're going to want a bunch of decimal places, and so we'll consider that. And then again, way later in Chem 163, we'll actually come back and use the masses of protons, neutrons, and electrons. So just remember that each particle in the nucleus weighs about 1 AMU. Now, the AMU has a very specific mass, and that mass, let me find that on Google here. So that mass is this. I don't have this in the slides because it's really not important, but just in case you were wondering. That's the definition of one atomic mass unit, is this number, 1.661 times 10 to the minus 27 kilograms. Or minus 24 grams if you prefer grams. That's fine too. So if I converted this to kilograms, this number right here, and then divided it by 12, I would get this number. Now, with that definition in mind, sorry, I moved my mic because I had to scratch my ear. With that definition in mind, what we can do is we can figure out the mass of any atom relative to a standard. And the standard that we use is carbon-12. So that's the mass of a carbon-12 atom. And we're going to set that equal to exactly 12 AMU. Then we're going to weigh everything relative to that. And the way that we do that is by using a device called a mass spectrometer, which I'm going to actually show you right now, I guess. Let's talk about the mass spectrometer. It's only 3 slides ahead, so let's just do that. What does a mass spectrometer do? A mass spectrometer weighs atoms individually, and it does it in the following manner. We input the sample, and then we heat it up. When you heat up the sample to a high enough temperature, it becomes a gas. Then what we do is we bombard it with electrons so that it gains a charge. Once we have gained a charge on our particle, the particle is going to accelerate through this tube, and it's going to pass through this magnet. The magnet will deflect any particle that contains a charge, because magnets and electric fields interact in that way. It is going to bend it based on the weight of the molecule. Heavier objects do not deflect as much. Lighter objects deflect more. And so what we need to do is we need to have the magnet deflect this particle so that it hits the detector like this. If it hits the detector, the detector will go, oh, I saw it. It weighs this much. And we're going to link the weight of the molecule that went through it with the specific strength of the magnetic field. So as I turn up the magnetic field, the particles will bend more and more and more until they hit the target on the detector. Since I calibrated this for carbon-12 to be exactly 12, I know what the magnet strength for carbon-12 will be, and then everything else is proportional to that. If something is twice as heavy, I need twice the magnetic field strength to bend it so that it'll go around the bend and hit the detector. If something weighs half as much, I need half the magnetic field strength, and so on. So I can weigh any atom to a large number of significant figures by doing this technique. And I wish that we did this in the laboratory, and we have like a few of them, I think, or maybe they're just gas chromatographs, I'm not sure. But I did tons of mass spec as a graduate student because it's very useful. So let's do an example here. Let's suppose that I weighed boron-10, and boron-10, I learned when it hits the detector magnetic field strength is set to 0.83442 times that which is necessary to get carbon-12 to hit the detector. So the mass of boron-10 must be this number, 0.83442 times 12, or 10.013. So now I know what the mass of a boron-10 atom is to many significant figures. And I also know all of these extra digits, so I don't just write 10 AMU and write down only 2 sig figs. Now I can get more sig figs, and that's useful to us. There's another reason that this is useful to us, and it has to do with nuclear chemistry. Again, we'll talk about that in 163. As you add more and more protons and neutrons, the result that you get is not simply the sum of their parts. Some of the matter is lost to energy, and that energy is used to bond the nuclei together. This is called nuclear binding energy. and it follows Einstein's equation E equals mc squared. Everybody wants to take 163 now because that's where all the cool shit happens, right? All right. So now we know how to weigh atoms individually. Let's get the mass of just a random sample of atoms, and then we can put that on the periodic table. So that will end up being the atomic mass. So this is the isotopic mass for a given isotope, and you determine this experimentally by using the mass spec. If you take the weighted average of all of the different isotopes that are naturally occurring, so not the synthetic ones, we don't care about the synthetic ones, because they don't last long enough on Earth for us to matter. If you take the weighted average of all the naturally occurring isotopes, you get the atomic mass. And that means we need the weighted average formula, which would be this. So the weighted average is equal to whatever percentage of the first thing you have times its amount, plus whatever percentage of the second thing you have times its amount, plus whatever the percentage of the third thing you have is times its amount, plus, and you do this over and over and over and over until you've done all of the things. Each of those is going to be an isotope. You're going to find out what percentage abundance it is and its mass, multiply those together, and then add that to the next isotope where you do the same thing, and add that to the next one, and over and over and over and over and over again until you've done all the naturally occurring isotopes. The sum that you get will be the weighted average mass, which we're going to call the atomic mass. And the atomic mass is what goes on the periodic table. The atomic mass is assuming that, hey, you are taking a random sample of this element. On average, this is what it will weigh in AMU. These averages tend to be very safe because any deviation in percentages locally will not occur to enough sig figs that we're going to notice it. For instance, all the carbon-14 in the environment comes from the atmosphere. It comes from carbon being hit with photons, I believe. And how does this happen? How do I want to explain this? So, nitrogen in the air actually absorbs a specific particle. It then undergoes, I want to say, let's see here, let me think about this. I want to say that it undergoes beta decay and you get carbon-14, and then you have carbon-14 that lasts in the atmosphere for a little while. If you were detecting a certain amount of carbon-14 in the atmosphere, it should be the same no matter where you go, and so we'll have the same contribution for your weighted average. For like uranium, for example, if I dug up a uranium ore in, say, Colorado, I would find the same percentage of uranium-238 versus 235 as I would if I dug up the uranium in, say, China, for instance. I should get 2x number of sig figs, the same number. And the reason that that's got to be the case is because atoms are so tiny. Even if you had tremendous deviation locally, to 4 sig figs, it would all be the same to our eyes. All right, so let's do a weighted average problem, and then I think that'll be enough for today. We'll call it a day after these two problems. All right, so first problem. Calculate the atomic mass of boron that should go on the periodic table using this data. So using that formula that unfortunately I just erased because text appeared over it. So I'll write it back here. So percent A times A plus percent B times B plus dot dot dot. I want you to tell me the atomic mass of boron that you calculate using the weighted average formula. And then what I want you to do is I want you to compare that number to the periodic table and see how close you got. So this data I've collected off of Wikipedia. Be mindful of sig figs, make sure you write out your units, and so on and so forth. But type your answer in the chat once you get it. We'll go over the answer in about 5 minutes. Actually, more like 3 minutes, because this is pretty straightforward. All right, 1 more minute. We'll go over the answer. All right. So let's go over here. All right, so let's write the formula down again. So the average mass is equal to, so the percentage of the first thing, which I'm going to call boron 10, times the mass of boron 10, plus the percentage of boron 11 times the mass of boron 11. And so that would equal 0.199 times 10.0129 AMU plus 0.801 times 11.0093 AMU. And so we could do each of those independently so we get the right sig fig. So 0.199 times 10.0129. So for 3 sig figs, I get 1.99 AMU. And then for this next one, which is also 3 sig figs, I get 8.82 AMU. Now I'm going to add to the hundredths place, so I can add all those together. I hit the wrong button. Hold on. 8.82 plus 1.99 equals 'there you go. We get 10.81 AMU. And according to the periodic table, which I unfortunately don't have up at the moment, let me grab that again. You'll see that we got real close. So there's boron in the corner there. We'll just put it over here. Not bad, right? All right, that's the easy type of problem that I can give you for using this formula. Here's a more difficult problem. There are two naturally occurring isotopes of chlorine. Chlorine 35, which weighs 34.9689, and chlorine 37, which weighs 36.9659. What is the abundance for each isotope? This is more difficult to do. In fact, it is significantly more difficult to do. So what I'm going to do, hold on, let me see if there's another one of these for you to practice afterward. Oh, there's not, unfortunately. So what I'm going to do is I'm going to give you this hint here. So you're going to need the periodic table. And you should know that both of your percentages add to 100%, right? Because whatever percentage of chlorine 35 I have, the remainder must be chlorine 37. So I'm going to give you a second to try this. Well, I'm going to give you 5 minutes, actually. And then I'll solve the problem for you, and I'll show you the correct way to do it if you don't remember this from 140. We'll go over the answers then. All right, one more minute. We'll see what the answer is here. All right, so I'm going to go over to this screen here. We're going to just put this down here in the corner for now. Let me get these isotopes up here on the screen. So there's that. And then finally, I need to actually click on chlorine so it shows up. Oops. There we go. All right. All right, how do I solve this? Because I know this number because it's right down here on the periodic table, right? It's 35.453. I'm going to add the extra 3 because I know it. However, the other numbers that I know are this number, which is 34.9689, and this number, which is 36.9659. I don't know these two numbers. So that makes this equation impossible to solve, doesn't it? I can't solve an equation with two variables that has a whole range of solutions. But what I also do know is that if I add the percentages of these two things together... Ooh, what did I do? I think I cut something. Ooh, that's not what I want. Undo. Undo. Thank you. I want to undo that. There we go. If I add these together, I should get 100%, right? Or 1.000. So what I'm going to do is I'm going to erase this. I'm going to erase this. And I'm going to replace these with variables. So this is x. And then I'm going to erase this. I'm going to erase that. And I'm going to replace that with a variable. This is y. And so now what I'm going to do is I'm going to solve for x and y, because I have a system of equations, right? So I can solve the system of equations. So I'm going to do the following. I'm going to say that y equals 1 minus x. Because I could just move this x over to the other side, right? And then I'm going to replace this anywhere I see y right there. So my expression now is going to look like this. M average equals x times M35 plus 1 minus x times M37, which then looks like this. Now I don't need these parentheses anymore because I don't have any more multiplication to factor in, so I got that. I'm going to take all the terms that are just numbers and move them to one side. Everything else can be on the right here. That's not plus, sorry, hold on. I could have left it like that, okay. So now I have that. I'm going to factor out the x. And then I'll just divide by that. No, there is not a formula to do this. You just got to do the algebra. So if I do this, I don't know why my pen is double writing. I think when I hit Control X or something, it screwed it up. But when I do this and plug in all the numbers now, so whatever my M average is, so that would be chlorine's atomic mass, so 35.453 AMU, minus whatever chlorine 37 is. Yes, you will get a negative number. That's okay. It'll work. Don't worry. I need to go like that. 9659. Divided by 35, which is 34.9689. No, don't put a parenthesis there. That's not where it goes. And then finally 37 again, which is that. And when I do this in the calculator, I get X equals so there's my top number. And I get 3 decimal places. So I get this. And then the bottom number, I get 4 decimal places. And then my units cancel out. These negatives become positive. My end result is 4 sig figs, and I get this. So taking that number all the way back up to here, if X is equal to the percentage of chlorine 35, then we got 75.76%. Y would be the remainder of that. And we know that 1 minus X equals Y, so I can say 1 minus 0.7576 must be Y, so there you go. That's a ton of algebra for a problem, isn't it? Isn't there an easier way? Yeah, of course there's an easier way. This is an online class. Punch these equations into Wolfram Alpha. Use an online solver. Don't make this too hard. I'm not going to sit there and grade your work on it when you're typing your answers into a... Yeah, there you go. Use Wolfram Alpha. Yeah. Don't do this. Like, this... Fuck this. This is algebra. Like, nobody wants to do this. I have to do it because I have to show you that it can be done. And if we were doing an in-person class, yeah, I'd make you do this. But this is an online class. No, just punch in Wolfram Alpha. In fact, I'm going to just do that really quickly for you just to show how fast that is. So I want those equations. I mean, I'm already over time, so I apologize that I'm going over here, but so here's my Wolfram Alpha equation. I'm going to cover that up because that's not what I need, but those two equations, I'm just going to type them in. So whatever the average mass was, which was 35.453, equals X times the mass of chlorine 35, which was this, plus Y times the mass of chlorine 37. So that's my first equation. So I go comma, and then I say X plus Y equal, oops, not 7, equals 1. Enter. Solve my equations. Oh, look at that. There's the solution. Oops, I scrolled past it. Look at that. That took literally 2 seconds, right? So totally worth just using an online solver. Now, it won't tell you the number of sig figs, unfortunately, because it's going to assume that whatever calculation it does is just going to print all the repeating digits, because, again, calculators don't know what sig figs are. But you can use these types of problems for sig figs, or accepting sig figs. You could use it to just check your work or to do whatever. And for what it's worth on Canvas, Usually I tell you how many sig figs to put in anyway, because Canvas, again, is like a calculator. It doesn't know what sig figs are. So there you go. Yeah, if you only have 4 sig figs for the mass, it turns out it really screws things up because of the subtraction. So, yeah. Adding in that extra 3 at the end, which I know, because I actually have a periodic table here in front of me that has it, gives me a lot more numbers to work with when I get to my result. So, there you go. That's how you solve that problem. When we come back on Thursday, we're going to put all of this that we did here together with the mass spec stuff. And I'm going to show you how to make a mass spec printout. So what does the mass spec show you after you fed something into it? You're going to draw a diagram for that. All right. That's what I got for today. Let's see here. So quiz number 1 is due on Thursday, and then lab worksheet number 1 is due Wednesday. Those are soft deadlines, so make sure you get those in. You do get a 24-hour period after those soft deadlines before the assignment closes. So if you absolutely need an extra day, that's what that's for. Otherwise, we're going to finish Chapter 2 this week. We're probably going to start Chapter 6. Chapter 6 is not that long, and then it is Chapter 3 forever, and ever and ever and ever, and we'll never do anything else other than Chapter 3. So look forward to that, I guess? I don't know. Thanks for coming to the lecture. I will see you on Thursday. Take care.